Let's see. I started the recording 25 seconds ago, according to that. I just hadn't said anything yet. I'm trying to remind myself I should say something as soon as I start the recording so that people have a volume check if they are watching the recording later. Okay, let's see. Did I get the right file here? Yeah, Wednesday, April 15th, tax day. All right. Oh, yeah. Thank you for that. Yeah, okay, cool. Thank you for that. I muted because I went to go stand and make sure that I turned off all of the oven thingies, the burners. I was just double checking. Thank you for that. Okay, I hope you can hear me. I did unmute. Thank you for that reminder. Let us do the following here. We are I need to be careful with my words. Done with functions. Don't celebrate too early. You do have an assignment on it. And in class today, you will notice that functions come up rather quickly. So everything in this class is actually very cumulative. I remember last semester when people visited office hours around this time of the semester, I would actually take one of my Play-Doh containers and show like a picture, like I'll try to draw my little picture of Calc 1 is like you've got limits here, and then derivatives kind of live on top of that, and then integrals kind of live on top of both limits and derivatives. And Calc 2, at least as we have it here, is like there's more integrals and there's sequences and series and there's like some vector geometry stuff and parameterization. And it's kind of like just a bunch of individual pieces that don't really much live on top of each other. And I mean, maybe I won't draw my Calc 3 picture or whatever, but like in this class, you've got propositions, and then sets live on that, and then relations live on that on top of the sets, and then functions live on that, and the thing we're about to look at, cardinality, lives on top of that. So all of these, what you'll notice in this class is things are very cumulative, not because I'm trying to be mean about it, it's just excuse me, it's just the nature of the subject area. So you'll see today that and tomorrow especially, you'll see functions come up. Um, just the round of announcements, I guess, just to make sure. Quizzes are dated Tuesday, but I'm through the end of the semester. You always have till the end of Wednesday to do it, recognizing how schedules work here. Responses are due Wednesday, so that's still the case. All responses for the rest of the semester are available. Some, if you want to get started right away on some, you can. Some of them might not make complete sense until a certain class or something like that, but at least you can take a look at them. Homework is due Thursday, and I just posted. So I have this, like, once I do my 2 hours of calculus in the morning, I have this 1 hour where I'm trying to get recordings to process before I upload them, and that's like a 30-40 minute process. And so then on the other computer, I was like, I could work on some clarifications or slash hints related to the homework. So I just sent an email as soon as I finished writing that. It was about 10 minutes ago. I would read through that document. I wrote it mainly in reaction to kind of the questions I got in office hours yesterday. By all means, still visit office hours today if you have questions and so on. But I'm trying to get to the key points, and I guess the thing that I should comment on is There was a really interesting comment that came up in office hours yesterday, and somebody said, "I didn't really think we'd have to like break apart that definition or that definition or that like." And I think the story is, yeah, if you don't, then why did the word appear, right? Like if there's a way to do the problem without bringing up that concept, then it shouldn't have appeared in the question. So every time you're looking at something appear and you go, "Wait, have I looked up that definition? Have I applied what that means in the situation?" I want to say like 98% of the time or 95% of the time. I mean, some really high percentage. Like the answer is yeah. You need to break that apart. Like a lot of this is peeling through definitions and applying, using versus proving, and doing those things. And at first, it seems like a lot, as you keep digging through the layers, like, oh, and then this and this, it seems tedious because it is at first. It just is, right? But like I'm just saying, don't give up. I encourage you to go through that process, and once you get through a question, actually, what you'll notice very often is like you step back and go, okay, that felt tedious at first because I got lost in am I using this or proving this, and I confused myself with it. But once you get through a question, I've noticed actually people say in office hours, happened last semester in person, happened online yesterday. People will say things like, oh, actually, that wasn't so bad. I mean, really, I think maybe I see some people signed in right now who were in office hours yesterday. They might vouch for that comment if you wish to or not. And then I just posted this, but it's called Mid-April Survey. You'll find it in the quizzes area of Canvas. Not required. I'm just trying to figure out what's working and what's not for you. I know that I wish I had done that even a week ago, but better late than never. Just let me know. I can't fix everything. Um, and I get that it's a good place to write some of your frustrations, and I won't be able to address everything, but among the other things, I hope this clarifications document helps. What I want to ask, just to kind of warm up our ideas right now, is this question. I'd like to look at A as the set of all integers, and then I'd like to define B to be the following set. C in set of integers satisfying the property that there exists D in integers such that um, D, sorry, excuse me, such that C is equal to 2D. Now I'm running out of room for where I want to put this, and I don't want to erase the announcements in case people join late. So let me also point out, like this is a usual, very useful, very good way to write things for proof, but we can go backwards. So this set could be rewritten in the format of, as you run through each integer d, give me 2d, and that's an element that belongs to the set. Right? So I know that we've often converted sets that are written in this format, kind of more in this format, and then here the fact that c, which is equal to 2d, is an integer, is just included as a bonus right now. And you'll also see this in the clarifications document I posted. Like you've got to be very you need to be like absolutely certain about how it is that you use or prove that an object belongs to a set based on its notation. Like this is stuff that we did actually not even the week before spring break, it was the week before that. And so this will just keep reappearing. Like unapologetically, sorry, we're going to deal with sets. And so what it means for something to belong to the set, both using and proving, is going to appear quite a lot. So I've got these two sets here, and I'd like to, I guess the question to ask is, which set is larger? Which set amongst A or B has more elements? And we're not going to directly answer this question right now. I'd like to just explore, and I'd like you to notice that the set A, which is just the set of all integers, I'll just put 0 in the middle, 1, 2, 3, dot, 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 negative 1, negative 2, negative 3, whoop, I didn't leave myself much room here, dot, 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 the other way. That's A, and let's look at what B is. If you stare at how B is written, either form, maybe this one's a little easier for us to just stare at it and write down some elements. So as you run through each integer called D, a thing of the form 2D is an element. So I think that capital B is a set of all even integers. Is that working for you to say this is 0, 2, 4, negative 2, negative 4, dot, dot, dot? So I hope you're staring at these two sets and saying maybe on the one hand, A has more things than B because like there's a 3 is an element of A, but it's missing from B. And the other thing maybe you might notice is every element of B is an element of A, right? B is a subset of A, or we could even, I think we introduced this notation that B is a proper subset of A. So not only is B a subset of A is not a subset of B, meaning that B has things that are missing when you compare it to A anyway. So first I want just sort of a warm up idea just to get your mind floating with the things, and we're not going to provide a direct answer to this question yet. We will just a page from now. So I want to remind you this old definition first. Let A be a set. So this was a while ago, but if there exists a non-negative integer let's call it n, such that A has exactly n elements, then we say A is finite. So I'm using the word finite as an adjective for sets. Of course, instead of saying A is finite, we could have said A is a finite set. That'd be another grammatical way to achieve the same idea. And the cardinality of A is n, which is written A vertical bars around it equals n. Otherwise, so I'm just doing the other part here. So it was the if there exists a non-negative integer n such that, and so if that if statement fails to hold, then otherwise we say A is an infinite set. Or just how about to match the grammar, how about we just write A is infinite? Cool. So that's a definition we've looked at. But what I want to do now is I want to note that when you look at this definition and apply it to the sets A and B above, A up here, let me circle this in blue, is not a finite set, right? There is no fixed positive integer n, which would say that A has that number of elements. A has more than that. Whatever n you're thinking of, if you're thinking of a fixed positive integer n, A has more elements than that. And for that matter, B has more elements than that too, right? There's an infinite number of even numbers, of even integers. So both A and B are infinite sets. Right, so you'll notice in the question up there, both A and B are infinite sets. And now we're gonna say a little more. So now, instead of just saying that sets A and B are infinite, we're going to try to talk about what are there situations where two infinite sets are going to be considered to have the same number of elements or not. And so here's the key definition. This is the thing. Chewing in this definition is going to take us today, tomorrow, Monday. This is an idea that's going to take us quite a lot of time to dig into. So here it is. Let A and B be sets. You'll notice in this sentence, you need two sets. There is no requirement in this definition whether A and B are infinite or finite or nothing. Just A and B are sets, any two sets. Then we say A and B are equicardinal. This is it's a fancy word just trying to say same cardinality, like equal, cardinal, cardinality, same number of things. If there exists a bijection from A to B. informally, so equicardinal, I'm using this word because you should think kind of adjective that applies to two sets at a time. But informally, you'll see language like A and B have the same cardinality, sort of written. So this is what a cardinality. So this is a 4-word phrase that's meant to capture the same as this one word equicardinal. So what's the point here is you see there's a couple of things we should talk about. There's a there exists. So if you're going to prove that two sets are equicardinal, you got to prove a there exists, right? Also, you see this word bijection hidden in there. A bijection is, or a bijective function, right? This is an adjective only for functions. So the thing is, there's functions already, right? So this is not, we left the section on functions and you can kind of forget about it because we're starting something new. No, this is a section that completely builds on what we talked about. So if you want to think of it this way, don't think of it like we just did 6 days on functions and we're on a new topic. Let's say that we're going to spend the 6 days we did plus these 3 new days, a total of 9 days on the topic of functions, and you can call these 3 days an application of functions. That's maybe the way to think of it. Okay, so I'm trying to say that to say, don't just try to ignore functions and go, oh, that was hard, I can just ignore this and be okay. That's not the way to take in the topic right now. So what's a little moral for what's going on? To prove A and B have the same cardinality, right? Let's say most of what you'll see in class today and tomorrow is you're given two sets. Maybe they're called A and B. Maybe they're called A and B, and then you'll be asked to prove, or we'll do it as a whole class, but we'll prove that the given sets A and B have the same cardinality, or are equicardinal. So how would we do that? Based on the definition of equicardinal, and I'm asking the whole class, right? Like, this is the thing where I know that right now there's this frustration of we need more examples of how to prove this thing, or like how to prove surjective, how to prove injective. You're going to see a lot of that in what we do, but let's talk about applying how definitions work, right? This first if is an if and only if. So if you are given two sets, they're described to you completely, and you need to prove that the two sets A and B are equicardinal, what is it we need to do? Okay, find a bijective function from A to B, right? Everybody okay with this? Because you got to prove a there exists, and a there exists means you got to make it, right? So you have to find, or yeah, let me. I agree with find a bijective function from A to B, but to just like really make the urgency of it, I'm going to say we need to make a function, right? We need to make. Find is, yeah, it works. Find, make, define a function. Maybe you could call that function by a name f if you'd like, from A to B. And not only do you define a function, meaning provide its domain, codomain, and rule, right? To fully define, you've got to provide domain, codomain, and rule. But in addition to this, and you have to prove that the function that you defined has to be a bijection, right? So up there. And prove F is bijective. So by the way, I do know from filling out of some things that people were like, I would like to see more proofs of injective, surjective. You're about to see them, okay? Because I'm going to prove to you, like what class is filled with today and tomorrow is just proof after proof of bijective, which is, by the way, proving injective and surjective. So you get both kind of at once. For the domain and codomain part, well, they're provided by literally the definition. One of the sets has to be the domain, the other has to be the codomain. So the key point is you have to provide a rule. And I need to maybe make the following comment, is you got to pick a good rule. So if you can't prove F as you defined it, based on its rule, is bijective, maybe you've picked a bad rule, right? You might need to change the rule. You might need to change the rule. Or you might need to, instead of or, your other option, second option. So instead of attempting to define a function f from a to b that's a bijection, your second option, your option 2, is define, maybe I'll call it a g, swap the domain and codomain, b to a, right? That obviously also has to be bijection. So before we dig into an example, or actually many examples today, I just want to talk about the idea of why this definition makes any lick of sense at all. Because at this point, right now, bijection is this kind of maybe slightly cloudy idea. And so I want to just kind of talk about this definition actually makes sense. Like these are the right words after the if. It's really should be that. So I want to talk through, this is kind of informal right now. So let's just say we're in this situation. If there really exists a function f, which is from a to b and is a bijection, then I want you to think about what this is going to give us. So what this really leads to is that means that every element little a in capital A has its one and only one buddy b that belongs to the set B, right? So let's think about it. Each input only has one output, right? That's this forwards thought has nothing to do with injective or surjective. That has to do with just being a function. Vertical line test, right? Each thing in the domain has only one thing in the codomain. Perhaps the more important thing right now to mention is that everything in the codomain, so every B and B, has its one and only one buddy, its preimage, little a that belongs to capital A. So this requires some talk. So why is there even one in the first place? Well, each thing in the codomain doesn't always have to end up being in the range, right? Each thing in the codomain doesn't actually have to be an output for your function, but it does if you have a surjective function. And so right now we're starting with, we've got a bijective function. So if you have a bijective function, then each element of the codomain has at least one input that produces that as an output. But then why the only one? Well, because that's the other part of f being a bijection, right? F is an injection, or f is injective, and that's saying that you can't have two different inputs go to the same output. So this one and only one business happens again, right? So this one and only one means not two, not zero. Each element of A has its buddy in B. Each element of B has its element in A. So think about it like, elementary school, kind of kids on the playground, or after a field trip, and they're trying to account for everybody, and so they do this to save time. It's like, everybody find your buddy. So like half the class is the A group, half the class is the B group, and if each person finds their buddy in the other group, then everybody, then both I know that the application there is then everybody's accounted for, or of course you could be missing two people who are just buddies in different groups. Oh, sorry, I didn't mean to go there. Oh, geez, okay. Sorry, let's get back to the whole point. Where we're going with this is, if there's really a buddy system, each person in group A has each person in set A has their friend in group B, and nobody has like two different buddies, like there's no like multiple assignments, then it should be that both groups A and B are the same size, right? So it seems to make sense here, right? So A and B have the same size. And I put this have the same size in quotes because we have formal language for this about cardinality and so on. But so it seems to make I hope this, at least this just general idea and explaining, like talking through what a bijective function really does for you, makes sense then, that these two sets A and B. If you can find a bijection, so the rule is good and you can prove that you have a bijection, it makes sense that the domain and the codomain of this bijective function should be considered to have the same cardinality. Hope that works for everyone. We'll start with a small example. So not the example we started class with, but I've got the set 3, 4 and the set 5, 6. Now, of course, both of these sets are finite. You know that the cardinality of both of these sets is 2. So, of course, it feels like these sets should have the same cardinality or should be equicardinal. But let's just, as a good warm-up to just not to reinvent the wheel with what we do later, let's do what we should do here. I'm going to define for you a function f from d to c by the rule input 3 is going to have output 5 and input 4 is going to have output 6. This is a bijection. We're not going to prove this is a bijection right now. We're going to do that with some more complicated ones in a moment. But just, if you know, this is a bijective function, right? Each codomain thing really appears as an output, and two different inputs don't go to the same output. So D and C are equicardinal. Okay, the point here is that I want you to note, just going through what we said back over here, you had to define a function. And so here I defined this function f. I told you its domain, I told you its codomain. Of course, those are kind of provided for free from the question, but I had to provide a rule, and the rule has to work. You can come up with functions with different rules that work and different rules that don't work. In fact, I think there's only one other rule for a function from D to C that works in this case. Okay, let's do a more full-on proof thing, unless there's questions. But I will write down the next theorem. So we'll go back to the original question at the beginning of class. So A is a set of all integers. B is a set. I'll write it in the format that's kind of more convenient for proof. So C and Z satisfying there exists D and Z such that C is equal to 2D. And so these two sets are equicardinal. Okay, so to prove this, again, this is, I don't know if I can say this enough right now. It's like the definition of equicardinal right after that first if starts with the phrase there exists, and it's there exists a bijection. So we need to define a function, right? We need to not only define a function providing its domain, codomain, and rule, but then we need to prove that the function is a bijection. So let f be a function from A to B with rule f of x equals, and I want you to give it a shot. If you can, without looking at my PDF, please, at least for right now. What would be, I want you to just stare at this for a moment. Nobody needs to type anything in the chat yet. I just want you to think about, like, how is it that you're going to start with as input x right there, anything in A, meaning any integer, and eventually, if you run through all of the possible inputs, get as outputs every even number once and only once. You get what I'm trying to, like, get you to think about how you would devise the rule on your own without giving away too much at the same time. Right? So I want everybody to just have a moment to think about that. Like, I want you to really, like, this is not a, oh, I'm just going to wait till he says it. This is like you know, coming up with the rule is the hardest part. Coming up with the rule for any of these is the hardest part. But I want you to really give it a go. Think about how you're going to start with, you're going to run through this thought experiment of x is going to be each possible integer, and if you apply whatever you say your rule is, you should end up getting every possible even integer in the end. All right, so 2x is a good conjecture. This is not the only thing that works, but this might be one of the easiest options that will work. So we will prove. In fact, as I was speaking, I thought of one other, and then as I kept speaking, I thought of way more. So anyway, maybe for another time, we will prove F is bijective. Okay, so to prove F is injective, again here the habits to form is the story is not ever about like, oh, there's a new definition, I don't know how to do anything with that. It's the definition is written in the grammar of what we did in the first 3 weeks of the semester. The definition of injective starts with a for all followed by another for all. Those for alls have as universe of discourse the domain. So we should pick two things in the domain, which is A. So I could write a Z, but I'm intentionally going to write an A right now. I think it just makes, so to prove this, we need to prove, I'll just, as a reminder of the definition, we need to prove for all, what should I call them? No, I don't want to use, I was going to use A's and B's, but that might look confusing. C's and D's might be confusing too. How about M's and N's? We need to prove for all two things in the domain if the outputs are the same. If f of m equals f of n, then the inputs are the same. Okay, so what I'm trying to get at is, so I don't want you to reinvent the wheel. I don't want you to fall into this kind of trap that sometimes people get in of, oh, we never proved a thing. Like this text dictionary definition translates into that right there. And so then as far as proving this statement, believe it or not, you actually had to prove things that were much harder than this in like homework 6 and homework 7, and some of those quiz study guides have questions that were already formatted in this format that made you deal with double for all and then an implication. You already had to deal with this kind of thing. So let's prove it, right? So to prove this double for all, usual thing, we let, allow the reader to arbitrarily pick whatever two things from capital A they want, and then now we need to prove an implication. So we should assume f of m equals f of n, and then we want to show m is equal to n, right? This is just like, this is all the, I hope what you're hearing is this is just all the usual story for how to prove a for all, how to prove an if then. So let's take a look at what we have. This capital A is just a fancy way of writing set of integers. So little m and little n are integers. From what we have here, f of m equals f of n. Maybe I'll just include this for clarity's sake right now. From f of m equals f of n, we get, let's replace the left side. F of m, based on the rule up here, is 2m. The right side, which says f of n, we can replace the right side with 2n. So dividing both sides by 2, we get m is equal to n. That was just what we wanted to show. That's a proof of injective. So then, to prove f is surjective, now I know the definition's still new-ish, even if it was last Thursday, actually last week Wednesday, so a week ago. I'll just write it down as a reminder right now that we need to prove the definition of surjective. Remember, I want you to think of it informally first, of everything in the codomain is really an output, and that should just build. It should just build the phrase, right? So it should be like everything, for each thing in the codomain, there exists a thing in the domain, so that when you apply f, you get that thing in the codomain, right? So if you look up the dictionary definition that we provided, that text is this text. So how do you prove this? You prove that, right? Again, just like injective starts with a for all, or rather injective starts with two for alls, surjective starts with a for all, though it's just one. So let's do what we need to do here. So to prove this, so let's let, sorry, I can't seem to erase right now. So let's just do, so let, I'll write one line down here. Let little b belong to capital B. So we're allowing the reader to pick whatever thing from capital B they want. Now we want to show that there exists an A in A such that f of A equals B, right? So we need to define little a, right? Because we're proving now there exists. How do you prove something exists? You have to define it. Not only do we define a thing called a, we shouldn't just define it randomly. It's got to work. Whatever we define for little a, we need to be able to prove that it's an integer, and we need to prove that f of a is equal to b happens. So at this point, you might already have a guess for what input you'll need in order to get the output to be little b. But if you don't have a guess, then the thing is, in any case, you have little b and capital B, and look up here. I'm going to scroll one line. B is written like this. I boxed it. You at some point need to apply the definition of B as well. So this comment you'll see in the homework clarification document as well, that you have to know what it means for what it means, how to apply this set, like something belonging to a set, like how to use and prove this. Always, it will just keep appearing. It's something from before spring break. So look, since you have little b belonging to capital B, there's this placeholder variable c for that. So I guess I'll just include this phrase from b and b just to help clarify where this is coming from. We get that there exists c in, no, sorry, there exists a d. There exists d in integers such that, okay, c was the placeholder that we're replacing with b, that b is equal to 2d. Cool. So that's applying what it means to belong to b, right? If you have this little b and capital B, and you see b is defined a certain way, and you never look there or do anything with that, something's fishy, right? So that would not be using the definition of b. So, okay, now let's keep the rule up here. I think I know how I want to define a. So I'm gonna, right? So we still need to prove this there exists. So what I'm gonna do to prove that is, right, let little a equal, and you might find this to be a little too much work. It's your call. I'm gonna let little a equal little d. Now d is back here. D, I'm just copying. D belongs to the set of integers. I just copied this bit right over there, and then set of integers, z, way at the beginning, that's equal to a. Right? So right up here at the very top left, z equals a. So look, if you follow what's going on here is little a. Another way to write that is a little d, but this thing belongs to capital A. That's good. We needed to prove there exists a little a in capital A. And then finally, we still need to prove f of a equals b. And so to prove f of a equals b, I'm just going to start with the left side, f of a. So f of a is f of d, right? After all, little a is little d. Little a is little d. These are just the same. That's how we define little a. And then f of d, well, let's look at the rule. What does f do? It doubles its input, so you get 2d. And 2d, just literally right above this, is a b. Cool, there we have it. A proof that f of a is equal to b. We've proved that f is injective. We've proved that f is surjective. This is a good place to pause. See if we're doing okay. So what we have going on here is the sets A, which we wrote earlier, right? Dot, 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 -3, -2, -1. We wrote it out this way. And B, which was just the set of evens, so, like dot, 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 -6, -4, -2, 0, 2, 4, 6. These have the same cardinality. We're going to say that these sets are the same size. So maybe you tried some of the optional problems earlier in the semester related to like people getting off of an infinite bus into a hotel that's already that's filled at infinite capacity, and some of these ideas are going to kind of keep reappearing. So I'd like to try another theorem if that's okay with you. I'll just start at the top of the next page. Unless there's questions on the last one. Okay. The subsets, bracket 1, 2, and bracket 3, 5. So these are both subsets of the reals. I just don't like starting a sentence with notation. Um, some people consider it bad practice to start with notation. So what I did was I tried to just talk about what kind of creature it is first. I could have said the sets, but I wanted to clarify that with this bracket notation, we're talking about interval notation, and these are subsets of the reals. Okay, these have the same cardinality. You get what I'm trying to talk about here is that if you look on a number line, so there's maybe 0, and then there's 1, and there's 2. So this interval right there, and then there's 3, and then there's 5, and this interval here have the same number of elements. Okay. Is this bothering anybody? Maybe it is. Okay, this cardinality stuff is kind of a little strange at first until you get used to what's going on here. So to prove this, I've got to define for you a function, right? I need to define a function where one of the two sets up here, we'll circle them in green, one of these two sets needs to be the domain, the other needs to be the codomain, and I need to provide a rule, but it can't be just willy-nilly. The rule has to actually work. In other words, based on the rule, we better have a function that is injective and surjective, and I will prove both of those things. So first of all, domain that set, codomain the 3, 5 set. By the rule, f of x is equal to 2x plus 1. Okay, so first of all, since f is an increasing function, why is f an increasing function? So here's the little bit of calculus that we use. Take a look at the derivative. F prime of x is just 2, right? So if the derivative or the slope is always positive, you've got an increasing function. And you can compute that f of 1, so I'm using the smallest input 1, and you plug that in, and you'll get f of 1 is equal to 3, and f of 2, the largest input, 2 is going to be the largest input we look at, you plug that in, 2 times 2 plus 1 is 5. So we know that because we've got a function where when x is 1, y is 3, and when x is 2, you have y is 5. We see that the codomain, we see that this interval 3, 5 is the codomain. What I'm trying to get at is we don't have. So yeah, let me write it this way. That is, for every x that you could pick in the domain 1, 2, based on how the rule is defined up here, that f of x computed using the rule I provided will always be between 3 and 5. If this did not occur, we would have a problem because then the codomain wouldn't work. So what I'm trying to say is here would have been a problem if I had said f from 1, 2 to 3, 5, and I'll just pick a rule that totally doesn't work, like f of x is equal to x plus 100. This is not going to work because if you just look at f of 2, that'll be 102, but that's not in the codomain, right? This is not in 3 to 5. So it's a kind of a quick argument that uses just a slight bit of calculus, but I hope you're convinced that if using the smallest possible input, you get an output of 3, using the largest possible input we'll use, which is a 2, you get an output of 5, and your function's always increasing, then all your outputs are always stuck between 3 and 5. Okay, so up to this point, I think an argument like this should be included for clarity's sake to really say, look, not only do we have a function with its domain, codomain, and rule, the rule actually works. Like the rule doesn't accidentally give you something not in the codomain. Like that's an important feature. It was a warning that was mentioned right at the beginning of class on Monday, for example. To prove then, now that we have honestly we have a function that is, domain, codomain, rule are all there. Is this function injective and surjective, right? Do we have a bijective function? So to prove F is surjective, okay, for surjective, this is everything in the codomain an output, an actual output. So let's let the reader pick y in 3, 5. You get why I've used a y. I think when I see a y, I think like, output. That's why I tend to like the variable y there for doing surjective proofs here. And then we want to show that there exists an input, and we'll call it x, in this input space in the domain 1, 2, such that f of the input, so that f of the input is equal to y. Okay, so what I'm going to do is I'm going to define, so if I need to prove for you this there exists, I need to define a thing, right, to prove that there exists. So I'm going to let x equal this fraction, y minus 1 over 2. Now, I need to prove to you that x defined this way, of course, this is going to be a real number. If y is a real number between 3 and 5, you subtract 1, you divide by 2, you're going to get a real number, but just having a real number isn't good enough. I better produce for you, by defining x this way, a number that's between 1 and 2. And if not, then there's a problem. Not only should the number be between 1 and 2, when you apply f, you have to get y. So there's a lot that I actually need to prove to you about this. So let me first of all prove to you that x is in the interval 1, 2. Okay, so since y is in the closed interval 3, 5. What does it mean for y to be between, so y to be in this interval? What we have is 3 is less than or equal to y is less than or equal to 5. Right? It's just what this interval notation is trying to get at. This is all the real numbers between 3 and 5. So you take this, it's like a double inequality because there's one there and one there, and we can let me subtract 1 on all 3 sides. So 3 minus 1, or 2, less than or equal to y minus 1, less than or equal to 5 minus 1 is 4. So I just, on all 3 sides, I take each of the things underlined in green, and if I subtract 1, I should have this new double inequality. And then I'm going to take all the sides of this inequality and divide by 2. So dividing by 2, you get 2 over 2 is 1, less than or equal to y minus 1 over 2. I won't simplify that in any way because it doesn't look like it will. 4 over 2 is 2. And so, look, I'm going to now replace x with the fraction y minus 1 over 2. So 1 less than or equal to x less than or equal to 2. So that's just a convenient way. Another way to say this is that x is in the interval 1, 2. Cool. So I've done there exists an x that's in the appropriate universe of discourse part. The next thing I need to do is I still need to prove to you that f of x is equal to y. Also, f of x equals, let's see, f of, you can replace the x with how we defined it over here, with y minus 1 over 2. And then what does y do to an input? You got to go back to the rule that's up at the top. F of input is 2 times input plus 1. So 2 times input, then a plus 1. And so you cancel the 2's and you have y minus 1 plus 1. And so you end up with y. That's what we needed, right? We needed to prove f of x equals y, and I've done that for you. There's f of x and there's y. All I did was I used earlier equations, so the argument should be sound here to have. So this proves, yeah, for any output between 3 and 5, I've shown now the input x between 1 and 2. I've defined the input you need based on the output, and I've proved that this input produces that output. So you have a surjective function. To prove F is injective, I think injective is actually easier here. So remember that starts literally the definition starts with two for alls. So we should let I don't know, P and Q belong to the input into the domain. So what was the domain? It's up here. It's 1, 2. And then remember that after the double for all, the definition of injective has an implication, and we are trying to prove this implication. So we should assume, so suppose that the outputs are the same, and we want to show that the inputs are the same. So what does it mean that the outputs are the same? So from here, the fact that f of p, well, what is f of p? What does f do? 2x plus 1. So 2p plus 1 equals, and then a way to replace f of q based on the rule is 2q plus 1. Now subtract 1 on both sides, so you have 2p is equal to 2q, and then divide both sides by 2, so you get p is equal to q, which was the thing we needed right there. So we've now proved over here f is surjective. In this 2 lines there, we've proved that f is injective, right? So we're done. We could already draw a box, but maybe I'll just say since f is injective and surjective, f is bijective. So it's domain and codomain. So this set and this set have the same cardinality, or are equicardinal. Box. That's the end of that proof. But I guess I should pause and see how we're doing. There's probably some questions. Maybe this bothers you? I don't know. Like, does this bother anybody? You want to type something? Like, how come this interval, like literally the distance, if you walk from mile marker 1 to mile marker 2, that's walking 1 mile. Whereas if you started at mile marker 3 on the interstate and you walk over to mile marker 5, you've walked 2 miles, right? So like these two intervals have different lengths, at least if you measured them with a ruler. Does that bother anyone? Or maybe you have another question, which is, where the hell did you get this rule? And if that's your question, I would like to answer that by saying I'm thinking of this domain as x values, and I'm thinking of the codomain 3, 5 as y values. So I actually have this little picture, x-axis, y-axis, 1, 2, 3, 5, right? X values are stuck between 1 and 2, y values between 3 and 5. I need a function that's going to be injective and surjective, so why not just straight line? This is a straight line segment. So you can create the y equals mx plus b, from this. That's all that happened. If you take the straight line, this is algebra, like high school algebra, right? If you just take up the 0.13 and the 0.25, you get a slope of 2 and a y-intercept of 1. And yeah, there's this entire line of, but we only want the portion when x is between 1 and 2. So we just take that part. But at least the rule is still the rule. We just adopt it from the whole line. So if that makes sense, now the motive, like the inspiration for this, you should prove that the set 2, 7 and the set 3, 14 have the same cardinality. Okay, I want to do one more. Just this one's a little different. It's kind of informal, so don't like overthink this one. But I've got I'm going to define for you a set C, which will be the set of x, y. So x and y here are placeholder variables. So ordered pairs in R2, satisfying x squared plus y squared is equal to 9. Question, what shape is that? Well, I write down the next set here. Somebody want to unmute and talk about that? Or want to write about it? D is negative 100 to 100, so that interval Cartesian product with negative 5, 5 union this other set. So the set with negative 100, positive 100, Cartesian product, the interval negative 5 to 5. Circle, yep, agree that capital C is a circle. So then C and D are equicardinal, or have the same cardinality. So C, the set C, is a circle of radius 3, right? So what I'd like to do, this is a proof in, I mean, it gets the idea across. I don't even know if I really want to put this in quotes or something, but let's just draw, right? So the set C, I'll do this in a new color. So in blue, that's not blue. Office hours people yesterday know that I had trouble with colors. I had to move on to like looking at pictures of puppies. So we've got a set C, circle of radius 3. I'll draw that in blue right there. Maybe I should have put in a tick mark. Let's just call that a 3 right there. The next set, let's do this in red, is a little more confusing, but like look at the first part. There's a union, right? There's one set in parentheses unioned with another set. But if you take a look, this is a Cartesian product, meaning create every possible ordered pair where the first coordinate is a number between negative 100 and 100, and the second coordinate, well, this is not an interval now. The second set in the Cartesian product here is just the two numbers negative 5 and positive 5. So think about it. The x-coordinate can be any number between negative 100 and positive 100, while the y-coordinate has to either be a negative 5 or a positive 5. Okay, so y-coordinate negative 5. That's down here. But the x-coordinate can be any number between negative 100 and positive 100. That line is meant to be perfectly horizontal. I just have not drawn very well. And then what if you use a positive 5 like that? Right, so maybe I should now mark my axes here that this is a 5 there and this is a negative 5 here. Okay, the other set, and we're unioning, so we'll just take both parts. It should be now the x-coordinate is negative 100 or positive 100. So here's x-coordinate positive 100, but the y-coordinate is between negative 5 and 5, any number between negative 5 and 5. And then, let's see, when the x-coordinate is negative 100, but the y value is any number between negative 5 and 5, you have that. Let me just extend the axes just a little bit. Okay, so I've got this, what is this, the flag of Japan, or Bangladesh, basically. And so there's this huge rectangle, right? It's the outline of the rectangle, these 4 red line segments that make the rectangle, and you have this tiny, tiny, tiny circle in the middle of radius 3. I mean, do you see how huge this rectangle is? Because the width of the rectangle is 200, going from x is negative 100 to positive 100. And now I want to show you a bijection, right? So what's my bijection? I need to show you the buddy system. Every element in C needs to have just one element in D. What you do is just start at the origin and just draw rays going outward. So wherever you draw, right, like, what is the bijection? I mean, I hope the picture is making some sense. My lines are not as straight as I want them to be. I'm saying that this element right here, that blue point, that intersection between the ray and the circle in that one spot, is assigned that output. And then this ray, this blue point, is assigned that red point. So this is clearly injective and surjective just from the picture, if you think about it, right? Each element in red ends up being intersected by one of these green rays. And you don't have, so that's the surjective part, and you have injectivity. You don't ever have 2 blue points being assigned to the same red point. That's what I got for you. We will definitely do more proofs, lots of injective, surjective proofs tomorrow as well. See you in office hours.